Okay, this one, number 55, is another one where I want you to pay particular attention to the word increasing and decreasing. And this one's a little more involved. This is something I expect you to be able to predict successfully. And it's, in order to do so, you have to go beyond simply memorizing something. What you're going to need to know is the underlying reason why the pattern exists. And please note, before we go to answer the question, it's in order of decreasing ionization energy. And what is ionization energy first? Yeah, the amount of energy or the amount of work that has to be performed to remove the outermost electron. So I should, it's sort of implied, I'm talking about first ionization energy, the first electron, the most easily removed electron. Okay? And so that is, and now this one, I want you to work on your scratch paper. You don't have to because there isn't very much space there to write the actual order. So in order to understand it, you're going to have to do the following thing on scratch paper. And so this, what you're about to see, does not go on the test. This is scratch paper stuff. You're going to need the following. Okay? And I'm going to start over here on the left-hand side. This is ionization energy. This is all scratch paper. Increasing ionization energy. And this would be, I'm going to start with, on the left-hand side, lithium. I'm going to go from lithium to, I'm just going to go for the entire row, and then we'll deal with the ones that are here in a little while. Lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine. I won't have neon, I'll just deal with these. Now, what factors influence, first of all, what happens to the size of the atoms as I go across this row? They get what as you go across a row?
Smaller.
They get what as we go across the row? Smaller. He said bigger. I just want to make sure everybody understood. It's smaller. Why? Because there's more positive nuclear charge in the nucleus. Now that nuclear charge, as we go from one element to the next, is increasing, but the amount of screening, and when I talk about screening, what happens as I go down a group? I'm an increase in size, right? Why? I'm going for each row corresponds to a principal quantum number, right? The first row's the principal quantum number n equals 1. That's the first row. The second row is the principal quantum number n equals 2. And etc. As we go down, each row is another principal quantum number. It's the old shell game. Each row corresponds to a completed shell, which we're going to come to find out gets a particular amount of stability from having zero orbital angular momentum when you have a filled shell, a closed shell structure, which gives that wonderful inert character we observed with the noble gases. Now, but for now, as I go across, they get smaller. The reason they get smaller is because the amount of shielding by the inner shell electrons from the completed shell, the closed shell, these are all built above a closed shell of helium electron configuration, the 1s2. Those are filled, they're lower lying, they're closer to the nucleus, and therefore that negative charge shields the valence electrons from the sum of the nuclear charge, because the negative charge cancels out some of the positive charge. So the amount of screening that's available is the same all the way across the row. As I go across the row, I'm increasing the amount of nuclear charge, therefore with the same amount of screening, the successive electrons as I go across the row are held more and more tightly. And therefore, I see a decrease in size as I go across the row. So that one trend is going to would suggest that that was the only factor. What would happen as they're held more tightly, is going to take more work or less work to remove them? More work. So I would expect the ionization energy to, in general, increase as I go across the row. However, that's not the end of the story. That's just the same explanation we're going to get when we start discussing size. It turns out the nature of the electron is very important. But at least I can deal with lithium. I've got one electron. So whatever the ionization potential is, it's going to be, let's just put it here. Now as I go from lithium to beryllium, I'm adding another electron. Obviously spin paired, filling the 2s subshell. And so now this second electron is going to take more work to remove, so I'm going to see that increase here. So I've got a general trend here. Now the next electron is going to be from boron, is going to go into one of the two p orbitals. Either the m sub l equals -1, 0, or +1 for your information. But doesn't matter which. Is it going to be easier to remove?
Yes.
Why? It's higher in energy. It's a p orbital. What do the p orbitals look like again? Dumbbells. They look like this. There's not an s orbital looks like that. S orbital has significant electron density near the nucleus. The p orbitals have no electron density near the nucleus. Okay, yeah. Well, I am off camera, but okay. The s orbitals look like this. The p orbitals look like this. Okay, look like an 8, and you can see how with the s orbital there's electron density near the nucleus, because this is just a sphere. The electron density goes all the way to the nucleus. Here with the p orbital, there is no electron density near the nucleus. There's more electron density localized further away from the nucleus. So it's further away. It's going to be more easily removed, and it's also going to be reflected in this orbital diagram. So I would expect a decrease in the ionization potential, and indeed it is observed. There is a decrease in the ionization energy. It drops below that of beryllium, but above that of lithium. Now, having paid the piper for the price for going on from boron to carbon, I'm removing another p orbital, so it's going to be increasing again. And then when I go from carbon to nitrogen, I would expect another increase. We're just following this trend. And now, what happens when I go from nitrogen to oxygen? What do I have to do? Because Hund's rule had me fill these with unpaired electrons. Now I have to pair them up. Now, this one is sharing an orbital. It shares the exact same region in space. The only reason they can occupy the same space is because they're of opposite spin. But there's a thing called repulsion that's going to cause them, they're negatively charged, they're going to be repelling each other, and there's a certain amount of work that has to be done for them to be forced into that location in space. And so that's going to give us, it's called the pairing energy. And so that means there is going to be a slight decrease because of that in the ionization energy. It's going to take a little less work because we're removing a paired electron. Now when I go from oxygen to fluorine, I've already paid the piper for that pairing energy, so I get another increase. And if I were to go from fluorine to neon, I would see it increase one more time. So you see I've got these trends of increasing with some dips in the trend. I go here, then I go down. It looks like the stock market on a good year. but what would appear to be not a pattern turns out to be quite the pattern. So it's not only, I don't want you to just memorize this. I want you to know why. And you should be able to draw this on your scratch paper and draw this on your scratch paper and thereby answer the question. Now, we're going to arrange these elements in order of decreasing ionization energy. So that which one's going to come first. So now we can answer the question. I'm going to answer the question over here. This is all scratch paper. Which one has the highest ionization energy of any in this series? Which one?
Fluorine.
The fluorine. Does everybody agree with that? So the fluorine has a greater ionization energy than what? Than the oxygen. Well, actually, the nitrogen is higher than the fluorine. I mean, higher than the oxygen. So it'd be fluorine, nitrogen, which is greater than oxygen. See, that's where people get it wrong. And this is, the actual order is that delicate. I expect you to be able to predict this. And I may ask for increasing energy, in which case you go the other way, okay? But, okay, now oxygen, what's next in our hit parade? Which one's next lowest in energy? Okay, so I gotta mark these off. I've got oxygen, I've got nitrogen. Yeah, I've got beryllium, which is greater than beryllium, which is greater than boron, which is greater than lithium. But now you see why. So this particular sequence emerges. You have to be able to draw this and draw this in order to understand why. If you understand why, you've learned a great deal of chemistry. This is what we're here to learn, is how to do this. It's to know the underlying reasons. It's all first principle stuff. Okay? So is everybody clear on that one? This would be the scratch paper work you're going to do. That's the actual stuff that would appear on the test. This simple order. Okay? Any questions? Yes?
Isn't it just the increasing ionization energies, like when you go across the periodic table, and then decreasing is when it's like going up further down?
No, that's size. Decreasing size as you go across from left to right. Increasing size as you go down.
Yeah, it's like the size too, but I don't know, my teacher or the professor last semester, he said the size smaller and then higher ionization energy, and then when it's like the size is larger, then you have like more.
Okay. You were missing part of this, weren't you? Did you leave to go? Okay. This is the actual sequence in ionization energy for the second row. And this is the reason why. One of it was size effects. The ones that are, the elements that are have more nuclear charge experienced by the valence electrons are going to be therefore held tighter. And so as I go across a row, there's the same amount of shielding by the inner core electrons, and so I see it decreasing as I go across a row. And as I go down a group, I see it increasing because I'm going to larger principal quantum numbers, right? And so each row corresponds to a different number in principal quantum number. Now, what happens, however, is in order to understand the trend, you have to be able to draw this diagram here, which is energy, and this is the orbitals. The two s orbitals and the two p orbitals. And so let's go, I'll reiterate this real quickly so we can show you why this trend is observed. Again, with lithium, I'm removing a 2s electron. Here's lithium. Now, the next electron is going to go into which orbital? For beryllium. it's got to go into the lowest energy orbital, which is S, and this one has to pair up. So the beryllium is I'm going to expect to see an increase in ionization energy, right? Now, when I go from beryllium to boron, the next available orbital happens to be a 2p orbital for all the p block elements. And so that means an electron goes in here for boron. Well, this is in a p orbital, which looks like this. This is an s orbital, which is spherical, right? Well, the s orbital has a significant electron density near the nucleus, whereas the p orbital, and I didn't draw a very pretty p, but that was the last question. This doesn't have any electron density. It has a node at the nucleus, and the electron density is spatially extended out in space. So it's further away, it's not going to be held as tightly, and it's reflected in this energy diagram where the p orbitals are higher. And so this is not going to take as much work to remove as one of these. And so therefore, I see a decrease rather than an increase as I go from beryllium to boron. But now as I go from boron to carbon to nitrogen, I've already paid that price. And so now I'm just dealing with the experience of the increasing nuclear charge, which is going to give me an increase in the ionization energies. But now why does it drop down here at oxygen? Well, what happens here? I have to place the next electron in. Where is it going to go? So I'm doing the opposite of ionization. I'm putting them in. Where is it going to have to go? It doesn't matter which orbital. It has to do what? It has to be paired. It has to be in the opposite spin. That means it doesn't matter which orbital it's in. It's going to be in this. It's going to occupy the same exact region of space with another electron. The only way they accomplish that is if they're opposite spin. But that still takes a certain amount of work to get those to be in the same place at the same time, because negative charges repel each other. It's called repulsion. And so that is going to require a little extra work. And so that I get that energy back when I remove it. So it lowers the amount of work needed to remove it, because I'm relieving that repulsion. And I had to overcome that repulsion to get them to pair up, what's called pairing energy. So I'm relieving my pairing energy. So there's another dip. Now as I go from oxygen to fluorine, I've already paid the piper. So I'm now just seeing, notice I have 3 basic trends of increase. And now I go from there to fluorine, and if I want to complete the thing to neon, I get there. And this is, in fact, what you would experimentally observe. And rather than just simply memorizing this, I want you to be able to draw this, understanding this, the energy diagram. We'll erase that. And also based on the principle of what happens as I go across. Okay, I'm getting an increasing nuclear charge. Okay? So I want you to understand the underlying principles. If you can draw this, then you have to read the question carefully, and I underline the word decreasing ionization energy. I could write the same question, put increasing ionization energy. We just reverse this order. But the sequence would be preserved. In other words, it's not, if I gave the sequence going bang, 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 it's not going to work. That's not what's observed, and I want you to be able to predict it. Yes?
When the ionization energy is increasing, is it always at the same rate?
Well, if we're going to get into, I would expect you to be able to draw the thing to scale. It's going to be, this is just an approximation. That's the general trend, yeah, no. There's going to be a general trend, though, that this is accurate as far as the trend. This is not drawn to scale. And so I would expect these lines to be approximately the same slope, but no.
In fact, they vary, though?
There'd be a slight variance.
Is there a trend to the variance, like as you go to a different shell?
That much I'm not certain of. We'd have to go look at the actual experimental numbers. But this is consistent with those, and the explanation is the explanation that is most consistent with the quantum model of the atom. Okay? And this is accurate. It's not drawn to scale, but it's accurate, okay? So please don't hold me accountable saying, but that, you had this slope. No, it was a different slope. No, I have no idea.
I was just curious.
Yeah, it's a good question. We can go look. In fact, it might even be in the book if they've got an accurate diagram, and you can tell me. So I'll throw that question back at you with that proviso. Let's see. But right now, I do know for a fact this is a solid trend because it's the underlying explanation I'm more interested in. Okay, so even though you're not going to have this supporting your answer on the page, this is on scratch paper, this is what you're going to have on the page. And the big pitfall after you've got these bumps in the sequence is decreasing or increasing. Got to ask either way. Okay? Any other questions? If there are no more questions, that's a wrap for this question.